Today we'll continue our talk on Unit 3 chemical names. The previous video we went from the name to the formula. Today we will go from the formula to the name. I find this one, having gone over the previous video, sometimes a little bit easier since you kind of have a little bit of the understanding on how to do the reverse. So naming an ionic compound is the opposite of giving the formula for that ionic compound. First thing that we will do would be to write the name of an ionic compound. And with this, there are two steps that we are going to have and or need to have involved. And first step is to write the name of the cation. Now, including Roman numerals if it is a transition metal, and we should probably add also if it is a lead or tin. Lead and or tin will also have the Roman numerals added to them as we move forward in how to name these. And so name the cation. So your ability to identify your metals, again, is always going to be important. Being able to look at the symbol, look at your periodic table, and to identify the metals from the nonmetals, because this is the biggest part, is if it starts with a cation or a metal, more specifically, then it is an ionic compound. If it is a nonmetal, that means it's going to be a covalent compound. So being able to identify the cation and sometimes more specifically, whether it be a transition metal. So if it's a transition metal, that means it has to have the Roman numerals associated with it to make sure that we know, and we're also then telling the others what charge that cation has. So what does the first step look like? Well, and it's pretty simple, as we have already explored, that calcium oxide, or CaO, we would name the first element first. So calcium. Again, we are only going to look at the first step. Now for the second example here, we have Cu, which is for copper, since Cu later copper. We can then have to identify that copper is a transition metal. Therefore, it is going to need parentheses. Now, which parentheses, what goes inside the parentheses is, in some cases, that's where the trick lies. That's where the ability to kind of look at the compound as the formula is written and being able to recognize some other things. Some of the things to also point out is that in calcium oxide here, we have two capital letters. Usually when you have just two capital letters, that means you have no polyatomic ions. In this one here, we have three capital letters, meaning we have a polyatomic ion. Now, if you have four capital letters, that is almost a guaranteed that you have at least one polyatomic ion, if not two polyatomic ions. There could even be the factor of having 5 of those, and that's just crazy polyatomic ion fun when that happens. So when we look at what number goes inside copper, we need to, maybe we'll just write it down on the side, and we'll come back to it and kind of be able to address if you wrote this, this is why. And so write down what you think copper might be inside those parentheses, and then we'll come back as we continue on. The second step is to write the name of the anion. Be sure to change the ending to IDE. We should have be a little bit of practice in this, and that in the previous naming of compounds, and that's covalent compounds, we had to change the ending of the second element to IDE. This is the same thing that has to occur in the ionic compounds. So to piggyback off the previous one, we would have calcium, and then we would write the anion oxide. Okay? And so there you have calcium oxide. There are no parentheses. We don't have to indicate that calcium has a positive 2 charge and that oxide has a negative 2 charge, because those are the charges that they always have. And so calcium oxide is all we have. Now calcium might be very close to the transition metals, but it's not horseshoes and hand grenades, so being close doesn't mean anything. So you need to have it needs to be in that groups 3 through 12 on the periodic table. All right, now coming back to this one where we had the previous, and we had the copper and we had our parentheses. Now SO4 is the polyatomic ion sulfate. Not what I have written down here. And the sulfide, it should be sulfate. So how do we know what Roman numerals to use? Well, we need to ask ourselves sometimes the following questions, of which we hopefully should be able to, if we don't know off the top of our head, be able to reason and or solve the problem. What is the charge of the sulfate ion? Now, if you don't know, it is information that can be looked up. Now, for the class that I teach, we usually always will have the sulfate ion on the back of our periodic table. Now, one of the other benefits for the class that I teach is that the anions, well, for the most part, any and all anions only have one negative charge. This is key. Being able to identify the charge that the anion is supposed to have based on the location on the periodic table or through memorization of your polyatomic ions. We can see that the sulfate ion should have a negative 2 charge. Now, when we ask the question, what number is written in subscript for sulfate, we get a little bit confused because a lot of us are going to want to say this 4. But that 4 that we see here is for the fact that it's the sulfate. And in some reality, though, we should actually almost, in a way, think about that sulfate as if it has parentheses around it. Wrote it in yellow and it's hard to see, but that's kind of what we want to almost do, is that it's in there. Because we shouldn't put parentheses around a polyatomic ion if there are just one of them. So the fact that there is nothing written on the outside, or the polyatomic ion itself is not in parentheses, indicates that there is actually one of them there. Now, what that means we have to do is we need to do the reverse crisscross. When we do the reverse crisscross, the one that is associated with the sulfate goes to the copper. The 2 that is associated on the bottom of the copper goes to the sulfate. Now, what this now does is tell us some information. is what number is written by copper now? Well, that 1 is written by copper, meaning we actually have copper 1 sulfate. We know this is the correct one because that 2, and that is subscripted by copper here, went to the superscript or the charge of the sulfate ion. So we did our reverse crisscross correctly. If we did not, say we had something written like so, well, we would have a 1 and 1 situation where we would look at this and say, well, I have a 1 down here and a 1 down there. If I do my reverse crisscross, I would say that the sulfate ion would have a -1 charge. I can look to verify whether or not that's correct. And I know that that would be incorrect because the sulfate ion is supposed to have a -2. So then I have to think of, okay, in what scenario would a -2 charge result in no crisscrossing? That would be if the cation had a +2 charge. So again, these ones can be a little bit tricky or a little bit interesting to kind of look at, and it takes practice to get good at kind of being able to look at and identify what we have to do to get some of these to work, because it's not always easy and straightforward. So let's try some out. For the first example, we see an Fe2O3. Now, some of you might have this growing on a car, either the one you drive or somewhere else, and a lot of that will depend upon where the car came from as how fast it happens. If we do the reverse crisscross, the 2 would go to oxygen, which makes sense. The 3 goes to the iron, which can make sense. And so when I go to write it out, and I write iron 3 oxide, everything works out. That 2 going to the oxygen is kind of my verification that I did this correctly. This is betterly or more commonly known as rust. And that's where sometimes common names for compounds are there, but we have to be aware of what they are. For the next one, we'll go to the right, and we see that we have the Al2S3. Now, Al is really close to being a transition metal, but again, it's not horseshoes and hand grenades, so therefore, we don't use that. We don't need to do the reverse crisscross necessarily because it's not a transition metal. And therefore, I can just write aluminum, and because I only have 2 capital letters, that S is not a polyatomic ion, and therefore it is sulfide. Moving down, I start with Mn, which a lot of times people always jokingly refer to as Minnesota. I have something in parentheses. This is the other way of being able to kind of say, oh, guess what I have? A polyatomic ion. And that's because that's what we go with. And so we have this ClO to identify that that's our polyatomic ion. So now we have that wonderful question, and we look at, well, there isn't a number written in subscript on manganese. Well, remember, by just writing the symbol indicates that technically there is 1. Therefore, when I do the reverse crisscross, the 1 goes up to the ClO, and the 5 goes to the manganese. Now, what polyatomic ion is ClO? It's in parentheses. Well, if we look on our periodic table, or on the back of the periodic table, we will see that it is hypochlorite. And because manganese is a transition metal, we need to make sure that we have our parentheses to have our Roman numeral, and then have hypochlorite. Notice that I did not change the ending of the polyatomic ion. The ending of the polyatomic ion stays the same all the time. We do not change the ending of a polyatomic ion unless the number of oxygen is changed. We do not change the ending of a polyatomic ion to IDE in any circumstance unless it's the oxide polyatomic ion. So we have to be careful. Let's go to the left. And when I go to the left, again, I have another thing where I see I don't have any number written in the subscript for Ti or titanium, so I write a 1 there. I do the reverse crisscross, and I see a 1 goes to oxygen and a 2 goes to the titanium. I should be concerned because that 1 goes to the oxygen, because the charge on oxide is a -2. This does not make sense. This is not correct. I know, and so we do is we write it out. Like, I know that titanium has some charge that's positive. I also will know oxygen is going to have a charge of -2. If I write a +2 here, I'm not going to get that formula. Because if I have that +2 there, the charges would cancel out. So I'm stuck in a conundrum. What happens? Well, if I wrote a 4 there and then did the reverse crisscross, I would get the answer of Ti2O4, which would lead you to one of the names that this goes by, and that you would say titanium for oxide. Now, what happened? Well, it was reduced. And that becomes very frustrating for people. Like, what do you mean it was reduced? You can't just reduce things. Oh, yes, we can. And that becomes, like I said, frustrating. So you have TiO2O4, which is reduced to TiO2. Now, that isn't even going to be the name that you would find if you Googled it. If you Google it, you're going to get the name titanium dioxide. And then you're even more confused. You're like, Peterson, I thought you told us that the monoditries are only used for covalent compounds. And you would be correct. This is where different naming schemes come into play. Now, what's even more interesting is if you're a geologist, you call it completely something else. You call it rutile. I think that's what to spell it. Now, if you go into the bathroom and brush your teeth and you look on the inactive ingredients, on the inactive ingredients of most toothpastes, you will see titanium dioxide written down. And why do we have titanium dioxide? It's because rutile has it's about an 8 or 9 on the Mohs hardness scale, so it's going to be really useful at scrubbing those teeth nice and clean. The other thing is, if you go down or find where you have your paint stored, one of the ingredients in paint is also titanium dioxide. And then people really get crazy and they go, oh my gosh, I'm putting paint in my mouth. No. Titanium dioxide has a different use for paint, and that is it's a binding agent. It's used to help bind the paint molecules together. It's a lot safer than lead. Who would have thought? So sometimes compounds have a lot of different names. So we have to be wary of that. So let's go to a different one that's a little bit more normal. CuCl2. Now, when we look at this, we can see that there is no number written for Cu, but there is one of them, so we write a 1. We do the reverse crisscross. The 1 on the chlorine would make sense because the charge on all group 17 elements is a -1. Therefore, the 2 on copper has to be true to give us copper 2 chloride. The next example, BaNO2 with the inside the parentheses with the 2 on the outside. Barium is not a transition metal, so we don't have to do a reverse crisscross, and so we would just write what it is barium. The fact that we have something in parentheses is again the red flag of going, hey, we got a polyatomic ion here. And this one we need to make sure that we're very careful to read carefully in that it's nitrite. Nitrate is a little bit more common, but it has one more oxygen on it. So it's barium nitrite. The next one, we have 3 capital letters. There's our indication that we have a polyatomic ion. Sodium, or Na, is not a transition metal, so no reverse crisscross needed. and therefore it would be just sodium sulfate. Which of the formulas does not represent a compound that actually exists? The compound that does not exist is the sodium phosphite, and that's because if I look at a reverse crisscross, that 2 would go to the phosphite, which does not occur because the charge on phosphite is a -3, and therefore D is the answer of the compound that does not exist. Now for a special group of compounds, and these are called the hydrates. Hydrates are a compound that contains water. It's a part of the crystal structure, and therefore we do need to make sure that it is a part of the chemical formula. It is known as the water of hydration, which is kind of weird. Most of the compounds that we have been naming are known as what's anhydrous compounds. Anhydrous means that water is not a part of a crystalline structure. So we don't really have too many times where hydrates are going to be a part of it. They're just kind of, we use these to kind of say, hey, make sure you're aware of these because it's good knowledge to know that this actually does occur. It is some hydrates are more common than the anhydrous. Some hydrates are very important in construction manners, which means the majority of people probably have a hydrate somewhere in their house. Calcium sulfate is an example of a hydrated compound. Calcium sulfate actually can happen in 3 different manners. One, calcium sulfate, the anhydrous. That's what you would probably guess and look at and be able to identify based on the name. You have calcium sulfate hemihydrate or basinate, which some people look at that and go, how do you get a half a water molecule? It's a part of all the crystalline structure, and how it repeats is where kind of like a half a water molecule is in between the crystalline structures of calcium and sulfate. That's kind of how that works, but that's a topic for another time. But the one compound that I'm pretty sure a lot of you do have, and that is the calcium sulfate dihydrate. Most people have this in their home. It is known as gypsum, or better referred to as sheetrock. And the water molecules actually in some manners will help slow down the deterioration of the sheetrock, and also be a flame retardant in that it kind of holds them at bay a little bit. Not very long, but just a little bit. And gypsum or sheetrock, when it gets really old, gets very brittle. It also gets really weird when it gets wet too, but that's because of another topic, and that would be the fact that it will dissolve and or dissociate based on other things. There are other hydrates, but I like to use this one just to kind of give you a real-world example of something that you would see in a number of different ways, and also one that you have in your home. Because if you go to the hardware store and need to buy some, gypsum rock, chances are you're buying sheetrock.